we continue to learn chapter 3, vector spaces. Okay, section 6, row space and column space. First, we say part 3, the column space. Example, find a basis for the row space and the basis for the null space for this matrix A. This matrix A is a 3 by 4 matrix. So in order to find its row space, the basis for the row space and a basis for the null space of A, so we need to use Gaussian elimination to transform A to its row echelon form. Then the non-zero rows will be the basis for the row space. And also from the equivalent system, we can solve AX equals 0 by UX equals 0, where U is the row echelon form. And then we can solve the basis for the null space of A. Okay, so in this example, the matrices A and U have different column spaces. We should be careful about this. However, their column vectors satisfy the same dependency relations. So because we have U2 equals 2U1 and U4 equals 3U1 plus 2U3, immediately we know that A2 equals 2A1, A4 equals 3A1 plus 2A3. Here, U1, U2, U3, U4 are the columns of the row echelon form of A. And A1, A2, A3, A4, they are the columns of the original matrix A. Because the two systems, AX equals 0 and UX equals 0, they are equivalent. So we have these same dependency relations for the columns of the matrix A and the matrix U. Okay, two row equivalent matrices have the same row space, but different column spaces. In general, if A is an n by n matrix and U is a reduced row echelon form, since AX equals 0, if and only if UX equals 0, their column vectors must satisfy the same dependency relations. We have this theorem, 3.6.6. If A is an n by n matrix, the dimension of the row space of A equals the dimensions of the column space of A. So think about this theorem. The dimension of the row space of A is defined as the rank, right? The rank of this matrix. And the dimension of the column space of A. How to consider about this? So the dimension of the column space of A, we can consider the independency columns, the maximum number of columns that are linearly independent. Okay, so you can consider solving the linear system AX equals 0 or its equivalent row echelon form UX equals 0. Okay, then you can find its columns that are linearly independent. Okay, so we see the proof. If A is an n by n matrix of rank R, its row echelon form U has R lead ones. The columns of U corresponding to the lead ones are linearly independent. These are the known results. Okay, let UL and AL denote the matrix obtained by deleting all the columns corresponding to the free variables. Okay. Since UL and AL are row equivalent, so ULX equals 0 and ALX equals 0, they have the same solution. So they are equivalent system. Since the columns of UL are linearly independent, it has only the trivial solution x equals 0, and hence the columns of AL are linearly independent. And since AL has R columns, the dimension of the column space of A is at least R, right? That is, for any matrix A, the dimension of a column space of A is greater than or equal to dimension of row space of A. And we can apply this result to A transpose, okay? And we will get the dimension of row space of A equals the dimension of column space of A transpose, because the columns of A transpose just come from the rows of matrix A. Just you write this in row vector and write here in column vectors. Okay. Okay, and because we know the dimension of column space of A transpose is no less than the dimension of row space of A transpose, and the dimension of row space of A transpose again equals the dimension of column space of A, because the column space of A comes from the row space of A transpose. Just you write one in row vector, one in column vector. They are essentially the same. Okay. Thus, for any matrix A, we have a dimension of column space of A equals the dimension of the row space of A. Because here you have a dimension of column space A is no less than the dimension of row space of A. And here you have, on the other hand, you have dimension of row space of A is no less than the dimension of column space of A. Okay, so we have this equality holds. And then we prove this theorem. Okay, now consider the dimensions of row space and column space. We have such conclusions. Let U be the reduced row echelon form of A. Then A and U have the same row space. We know this. And we emphasize that A and U have different column space. However, their column vectors have the same dependency relations. Okay, and the columns of U corresponding to the lead ones are linearly independent, and those columns of A are also linearly independent. Okay, now we consider basis for column space. We can use the row echelon form U of a matrix A to find a basis for the column space of this matrix. We first determine the columns of U that correspond to the lead ones. The same columns of A will be linearly independent and form a basis for the column space of A. Here, we emphasize that in general, U and A, we have different column spaces, and we cannot use the column vectors from U to form this basis of A. Okay. Here is an example. Ask you to find a basis for the column space of A. So you can use Gaussian elimination to transform this matrix A 4x5 matrix to its row echelon form, or you can do further to form the reduced row echelon form. And you find the columns that contain the lead ones. Those columns are linearly independent for this matrix A. They form a basis of this matrix. Okay, you return back to this matrix A, and the corresponding columns form a basis for the column space of A. You cannot use the columns in the reduced row echelon form U, but you can return back to matrix A and find those columns corresponding to that lead ones. They form a basis for this column space.